Hello friends, in this session we will be discussing about Cobb-Douglas production function and the properties of this production function. Cobb-Douglas is the name of economist who has given this production function referred as Cobb-Douglas production function, one of the homogeneous production function which we will be doing. It is explained as x, which is nothing but output, is equal to B naught L to the power B1 and K to the power B2. Here, L level of output, L refers to labor, K refers to capital, and B naught, B1 and B2 are the coefficients. B1 and B2 is referred to as coefficient of labor and capital respectively, and B naught is referred to as efficiency coefficient. We will be discussing about each and every detail about the coefficient, about the properties of Cobb-Douglas production function as we move on. Let's start with the first property of Cobb-Douglas production function, which is referred to as marginal product of factor of production. As you know, are taking two factors of production here, labor and capital. L refers to as labor and K refers to as capital. Now MPL is equal to labor, that is MPL. So marginal product of labor, that is MPL, we will first derive from this production function. X is equal to B naught L B2. Okay. Now as the formula says, MPL is dx by dl. That is, when I differentiate x, that is output, with respect to L, I get to have what is MPL. My x is nothing but B naught L B1 K B2. Now I have to differentiate this level of output with respect to L. Now those who are aware of how we do first differentiation would find it very easy. Those who are not aware how first differentiation is done, I'll just give you one small example of first differentiation and then get back to this particular formula. In case of first differentiation, if I have x to the power n and I say differentiate, say this is y, differentiate y with respect to x, delta y by delta. The formula is x to the power n minus formula for level differentiation. This is basic maths which we do. Now this same formula we will be applying and differentiating this x, that is x level of output, with respect to L. So x to the power n gives us n, x to the power n minus 1. When I differentiate x with respect to L, my other factors like B naught, K, B2 will become constant for me. So I'll keep B naught, K, B2 as constant. I'll differentiate L to the power B1 same as x to the power n by saying this would result into B1 L B1 minus 1. This is how I differentiate my x with respect to L. Write this whole in terms of x. My x is B naught. I have B naught here, so I have B naught first. L B1. I have here L B1 minus 1. The same thing can be written as L B1 into L to the power minus 1. Because in multiplication the powers are added. So this is nothing but L to the power B1 minus 1. Now I will put this L to the power B1 as separate and L to the power minus 1 I will take as separate out of the brackets. Now, yes, K to the power B2. So, I have K to the power B2 also with me. Whole this differentiated x, I am left with only B1, which we have not used here. So, I will put this B1 separate. Now, if you see this B0, L, B1, K, B2 is nothing but x. L minus 1 can be written as in denominator only L, which is nothing but plus 1 with the power into B1. Now this x by L by formula is average product of labor. That means my marginal product of labor for Cobb-Douglas production function is equal to B1 into average product of labor. That is what we get as our result. Now in the same lines, I will be finding now marginal product of capital. Now we will be differentiating this x with respect to k. Now when I differentiate this x with respect to k, or I say marginal product of capital is dx by dk. On differentiation again, leaving k, others I will keep as constant. So B0, L, B1 kept as constant. K to the power B2 when differentiated becomes B2 k to the power B2 minus 1. Again the same formula of x to the power n I have applied here. Now if I say I want to write this in terms of x. So let's start with x. It has first as B0. We have B0 here. So B0. Then it has L to the power B1. We have L to the power B1 with us. Then it has k to the power B2. Here I will write this same figure as k B2 into k to the power minus 1. So I will take k B2 from here and put this k to the power minus 1 outside my brackets. Now what I am left with, I have taken B0, LB1, KB2, K minus 1 outside, and now left is B2. So I will keep it here. In my brackets, what I get is nothing but x, K to the power minus 1 in denominator and written as K into B2. Again, x by K is nothing but average product of capital into B2. So we can say marginal product of capital for Cobb-Douglas production function is equal to B2 multiplied by average product of capital. This was our first property of how do we define marginal product of factors of production, which we took two here, labor and capital, in case of Cobb-Douglas production function. Now we will be doing the second property, that is marginal rate of technical substitution, which I can write as MRTS, that is nothing but marginal rate of technical substitution. This we have discussed before is nothing but slope of isochord. So marginal rate of technical substitution has the formula of MPL upon MPK, that is marginal product of labor upon marginal product of capital. Now from our first property, we derived the value of MPL and MPK. So what I'll do is, I'll just put the value of MPL and MPK. MPL I said is nothing but B1 into APL, and MPK I said was B2 into APK. That means it is B1 into X by L upon B2 into X by K. Now when I take this to the numerator, first of all X gets cancelled and what we are left with is B1 by B2 into K by L. So our property says that marginal rate of technical substitution, which is slope of isocon, is nothing but B1 by B2 K by L. This is our second property of Cobb-Douglas production function. Let's go on to the third property. Our third property talks about elasticity of factor substitution. How do we find elasticity of factor substitution? Now, concept of elasticity we have discussed in initial units. As per the formula, our elasticity of factor substitution is nothing but percentage change in K by L upon percentage change in MRTS. Now this MRTS has come from our second property. Now I can write percentage change in K by L as delta K by L upon initial K by L. This would be as a percentage change in K by L. 100 of course gets cancelled from numerator and denominator. And percentage change in MRTS can be written as delta MRTS upon MRTS. Now what we will be doing is we will be just putting the value of MRTS from the last property which we have got. So I'll write again here as delta K by L upon K by L. This is my same numerator which I have copied, and here it will be B1 or say delta B1 K by L upon, now this delta I have taken because of the delta sign which was here in delta MRTS, and this will be B1 by B2 K by L. Now here what you realize is B1 by B2 gets cancelled in itself when it comes to numerator. K by L also gets cancelled. So what we are left with? 1. Now 1 means that this function has or is perfectly substitutable function. That means Cobb-Douglas production function is perfectly substitutable function when I get this value of Cobb-Douglas production function as 1. This was my third property, that is elasticity of factor substitution. Now let me shift to the fourth property. Fourth property talk about factor intensity. Fourth property would talk about factor When I say factor intensity, since you are aware of the fact that we take basically two factors, labor and capital. So what we want to know is whether my production which is taking place is labor intensive or it is capital intensive. So how do we come to know that production is labor or capital intensive? For that we take help of the coefficients of labor and coefficient of capital. So B1, as you are aware, is coefficient of labor and B2 is coefficient of capital. Now my ratio B1 by B2, if this ratio is high, that means my numerator is more than my denominator. That means value of B1 is higher than value of B2. So automatically the level of labor employed is more than the level of capital. So this gives me a situation where it is labor intensive production taking place. The opposite will hold true. That means if B1 by B2 is low. That automatically means that value of B2, because this coefficient of capital is higher than coefficient of labor. And when coefficient of capital is higher, that means the production which is taking place is more capital intensive. So it is the ratio of B1 by B2 which helps us in deciding what is the factor intensity of that production which we have done. This was our fourth property. Now let's go on to the fifth property. Fifth property talks about efficiency of production. When I say efficiency of production, I am trying to give an example where there are two firms going for production with equal amount of raw material, with equal number of labor, with exactly the same quantity of capital. Still, the level of production of maybe firm A is better than the level of production of firm B. That kind of a situation can always arise, where my labor, capital, B1 that is coefficient of labor, B2 that is coefficient of capital, all are same. My raw material, my variables or factors of production, everything is same in both the firm A and firm B. Still, firm A is giving me a better production than firm B. Here it is B naught, which we efficiency coefficient, which helps us in deciding that whether or say which firm is more efficient. So reason why firm A is giving me a better production than B, irrespective of labor, capital, B1, B2 being same, is because in A firm B naught is high. That is, the coefficient of efficiency is high in firm A. That is why firm A is performing better or say is more efficient than firm B, even though their factors of production, their raw material and rest everything is the same. So this is reflected as efficiency of production. Now last property, that is the sixth property of Cobb-Douglas production function, would be returns to scale. That is, how do returns to scale in case of Cobb-Douglas production function. Now we all know Cobb-Douglas production function is written as B naught LB1 K B2. Now, and we say this Cobb-Douglas production function is a homogeneous production function. When I say Cobb-Douglas production function is a homogeneous production function, it has a property attached to this homogeneous. Homogeneous in case of this production function means that in case I multiply this whole function, or for that matter any function which is a homogeneous production function, by a factor which they refer to as small k. It can be any factor, it can be small k, small m, small p, it can be referred by any variable. But in case I explain this by small k, I say when I multiply my main function by a factor small k, and in the end I am in a position to factor it out. Factor it out here means I can take it common. That means my production function is homogeneous. So in case of writing Cobb-Douglas production function, I'll be first explaining with the help of simple function. Suppose the function is x is a function of labor comma capital. Now if I say x star, here I multiply this by small k. That means I am increasing my labor and capital by this small k. So I multiply my function by a factor which is small k. I should be in a position to factor this small k out. That means I should be in a position to take this small k as common in case this particular function is a homogeneous production function. So if this situation is possible, we refer to this function as homogeneous production function. Now assuming that yes, Cobb-Douglas production function is a homogeneous production function, we will be putting this property in this particular function. Now let's come back to x is equal to b naught L b1 k b2. Now I'll again say x star, where I will be inserting 1 or I will be multiplying this function with a small k factor. That means b naught small k L b1. This b1 would come as common coefficient of k and L. Small k capital K b2. Now I said if this is a homogeneous production function, we should be in a position to factor this small k out. Now when I factor it out or take it common, this small k will be having power of b1 here and power of b2 here. That means it will be k b1 into k b2. Small k b1, small k b2, rest remains the same, b naught L b1 and k b2. Now when our base is same, the powers are added. So this is nothing but k b1 plus b2, b naught L b1, k b2. Now this is the resultant which we have got of x star, which I said is a homogeneous production function. Now this b1 plus b2 can be written as k to the power v, L to the power b1, k to the power b2. Now here v is nothing but b1 plus b2. Now we have derived the value of v till here. V is b1 plus b2, which is addition of coefficients which we have taken out common with the small k when we multiplied this with homogeneous production function. Now coming back to what we actually had to prove. We had to prove in this property about returns to scale. What is the value of returns to scale in case of Cobb-Douglas production function? When we discussed production with you and we discussed returns to scale law, I mentioned there are 3 types of returns to scale: increasing returns to scale, decreasing returns to scale, and constant returns to scale. So whether this homogeneous production function will have increasing, decreasing or constant returns to scale, we will come to know with the help of this V, that is summation of the coefficients. Now if this value of V is equal to 1, I say it is constant returns to scale. If this value of V is greater than 1, I say this is increasing. This sign is for increasing returns to scale. If this value of V is less than 1, this is decreasing returns to scale. So to find the returns to scale situation of Cobb-Douglas production function, we had to first find V, and V we could find by adding the coefficients of labor and capital, that was B1 and B2, and this was taken as common after multiplying that whole production function with your small k, that is a factor, and this was because it was a homogeneous production function. So this was the last property of Cobb-Douglas production function of returns to scale, which was found with the help of value V. Thank you.